Hey Doc, what's cooking today? Doing all right? Tired? Why? Oh, they're giving more homework than I am? Okay, I see. So I can give more homework. Well, guess what? You're not going to have an assignment today. Yeah. You will have one on Friday. I need to get through the rest of the slide set. So if you wanted to start early, just so I don't forget, the assignment Friday is going to be read chapter 2 and then do some problems, but it'll be the first set of problems. So actually, you only really need to read the first chunk of chapter 2 if you're pacing it. But if you wanted to start reading chapter 2, you could. But I'm not actually giving you an assignment today.
Do you have any idea how long it is compared to chapter 1?
Ish, the same. I mean, how long was chapter 1? 40 pages or something?
45.
Well, technically, it started on 20, so 21.
Okay. So I think chapter 2 ends like at page like 90,
Okay.
something like that. But you could pace it because like I think I'll probably, if you wanted to look ahead, I'll have to look at how long I think the problems will take, but I'll probably give you between the first 5 and 8 questions at the end, starting chapter 2. At the end of chapter 2, those questions. So just as a foreshadowing, look ahead, what's kind of coming next. Exciting news, though, we do get to talk about forking children. Kind of sounds funny on the ear, doesn't it? We're going to be talking about the fork system call, which spawns child processes. What's up?
So that didn't make it better.
That didn't make it better. Well, when we get to it, I'll probably tell this again. But now that you kind of know a little bit of background on it, years ago, I was a system administrator at Western Illinois University, and me and the other Unix sysadmins were out at breakfast. And we're sitting there talking about this program we wrote called the Reaper, which reaped the children that had already been forked. So we're having this whole conversation talking about reaping children and forking children and all that stuff. And there's this old couple sitting at the table behind us. And they get up and just rip into us. So then we explained, like, oh, we're so sorry. But, we were oblivious to the fact that we were even saying anything. Ultimate geekdom, right? Okay. Yeah, but that was kind of funny. Last year, when we were talking about, we had a slide we were reviewing for a final or something, and there was a slide up, and it was actually forking a child, and it was in a box on the screen. So I think it was Tim Huseman brought up that, brought attention to that. So we've heard them all is what I'm getting at. Okay, so let's kind of zip through the rest of kind of this review stuff, preliminary stuff from chapter 1. So, some of these things we've already discussed, so we'll kind of fly through them a little bit. But, computer system organization, if we think about computers, we're all pretty familiar with that. There's a CPU, there's going to be and this is from the operating system perspective. So we have a CPU, we're going to have disk controllers, which is going to be software, or a combination of software and hardware that ultimately works with the hard disks. We're going to have a USB controller, again, a combination of hardware and software. So software drivers, which know how to manipulate the USB generic hardware for dealing with a whole bunch of USB type devices, mice, keyboards, printers. Okay, just thinking about the layers of our operating system. And then you're going to have a graphics adapter, and again, that comes in the form of hardware, graphics cards, and then the software that drives them. All right, and when we think about the history of operating systems, we're going to have at the core of all these drivers this idea of a VGA compatible graphics card. So every new hardware that comes out is going to have this lowest common denominator that should work with any operating system. So for those of you who have ever gotten one of those really expensive gaming graphics cards, when you first put it in, it gets generically identified by your operating system, and it's probably running at like 640 by 480 resolution or something like that, and sometimes even like monochrome image, like not even like color, or something along those lines, right? And then you actually install the super special top secret ATI or NVIDIA driver, and it starts looking good, right? That's when it starts knowing what differentiates this the supercomputer GPU to the generic thing from 20 years ago. So that's what's happening there. Okay, and then so we would usually refer to this whole thing here, this whole area of CPU, disk controller, USB controller, as kind of something called the bus. Okay, so it's this giant interstate, if you will, and they all have to be able to interact with our memory. We kind of mentioned that last time, where we think about memory as being fast, okay, as opposed to hard drives, which are relatively slow. So even by today's standards, if you're a gamer or something like that, you're starting to move towards the solid state drives because they're faster for hard drives. Okay, they are faster than our mechanical hard drives, but they're nowhere near the speed of our system RAM, which is nowhere near the speed of the various caches and the registers. As we get closer and closer to storage spaces for values, so closer and closer to memory, as we get closer and closer to the memory, to our CPU, things get faster and faster and more expensive. I think we mentioned that last time. Okay, so that's the punchline there. Okay, and then again, like last time we mentioned this idea of starting to think about our operating systems as resource management tools. We want to think about our computers as just a big set of resources. And some resources can only be used by one program at a time. Other resources might be able to manage multiple things at a time. I/O devices and CPU stuff can both happen concurrently, but sometimes those have to wait for each other, right? So I/O being reading stuff in and input and output from the user. CPU being the number crunching dude that's doing stuff. Well, sometimes the CPU could be going through a program one line at a time and ultimately hit a part where it needs to get something from the user. Well, now you have a chicken or the egg problem. So that's where the CPU then gets interrupted somehow. We'll talk about the details of that. But the CPU has to say, I can no longer go any farther with this particular program because I need something from the user. And I'm not going to just sit here and wait for the user because who knows how fast the user is going to respond. So the CPU is going to move that program off of the CPU so that it can go interact with the I/O subsystem and then start working on another process on the CPU where it can actually get work done.
So where does it move it to if it's moving off the CPU?
For right now, let's just say a staging area for doing I/O.
Is it in memory?
It'll be in memory. Yeah, everything that's kind of being manipulated by any of our resources on our system is going to be staged in memory. Yeah, memories are fast place for holding big things.
So is the cache memory that we've been talking about, is that a physical part of the CPU?
It can be. So I think last time I mentioned L1, L2, L3 cache. Yeah. So L1 and L2 definitely physical parts of the CPU. It's onboard memory that lives. It's a local restaurant establishment on the CPU.
And would every CPU have that?
Yes.
Okay.
Oh, every modern CPU.
Okay.
Yeah, when you talk about the evolution of CPUs, the way back, they didn't have L1 cache. They only had what are called hardware registers. And think of hardware registers as tiny little variables. It's kind of like hardware variables. Okay, but CPUs have a very limited number of those. We'll talk about those, but those are going to be your fastest, most expensive, and also smallest memory locations. So then for handling some more powerful tasks, that's when they started adding the caches, L1 and L2 cache, which, each one is kind of a little bit. So if we think about L1 cache would be like the storage area that's here in Mech 1. We can get to stuff here in Mech 1 faster than we can get to Germantown. Germantown's L2 cache. A little bit farther away. It takes us a little bit longer to get there. But is Germantown bigger than Mech 1? If it's not, let's assume it is by this example. It isn't? What's bigger than, well, we can go south, I guess. Glendale bigger than Mech 1? Fox Point bigger than Mech 1? Germantown's bigger than Mech 1 in this example. It's the greater metropolitan Germantown area. Okay, so typically L2 cache is larger than L1 cache, and also, relatively speaking, slower, but farther away. So there's a longer bus ride. So again, if we think about this as the bus, we have a longer drive to get to that memory. So there's latency moving stuff back and forth between it. So if we want stuff to be really, 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 really fast, we put it in hardware registers, which are right by the CPU's core. We want it to be pretty fast, but we don't want to use up our hardware registers. It's L1 cache, then it goes to L2 cache. L3 cache actually will be a physical part of the CPU, but it's actually for sharing stuff between multiple CPUs, multiple cores. So but all kind of in the same world. All right. Each device controller is in charge of a particular device, whatever. That's what we were saying here. These controllers, so they come in the form of hardware and software. It's like a combination. Local buffer is another name for memory. So most of these device controllers have their own little onboard memory that allows them to kind of collect stuff even when they're not ready to deal with it. So a buffer starts filling up so that the hardware controller always has something to do, something to feed off of, but can't get overwhelmed by dumping too much stuff into it. Make sense? So that's what buffers are as a generic term. CPU moves data from to main memory from local buffers, so everything gets staged in main memory, like we said. From device to local buffer controller, same thing. And then these are these interrupts we talked about, where the CPU gets notified that either something's ready or something's waiting, and things like that. We'll talk about all that stuff in deep detail when we get into CPU management. I'm going to talk about this later too. So these are how interrupts work at the detail level, interrupt vectors and interrupt-driven stuff, and it's relatively unimportant. Just a fancy way of saying something that's pretty easy. CPU gets interrupted when it can't do more work. End of story. Okay, the job of the CPU is to stay busy 100% of the time. So if it runs into a wall where it can't go any farther with the current task, it gets interrupted, throws that to somebody else to work on it, and starts working on something else. That's the whole interrupt world. All right. Same thing here. I'm just skipping these. We'll come back and deal with them later. Deal with those later. Okay, so we start talking about I/O stuff and system calls. So this is that I/O subsystem. So I/O starts, control returns to the program once I/O is completed. So we had our interrupt. The program left the CPU. It's now waiting for user input, or waiting for some kind of input. It doesn't have to necessarily be user input. It could be the user's been asked to type something. It could be we need to hit the network interface card to hit the internet and go and download some file or something like that. Some sort of input-output that is going to stall the CPU, at least temporarily, needs to be done. When we get a little deeper into this, we'll talk about multi-threading. So sometimes we're okay, we actually let the CPU know that we're going to go and do this on the side, but you can keep working on this part of the application. So this gets down to something called blocking and non-blocking computing. So when we spawn off a thread, a worker bee, as I've referred to them in some of your other classes maybe, that's a secondary minion who's going and doing things, but not blocking the rest of your program. So your CPU can keep doing stuff. Okay, so that won't force an interrupt. That forces the birth of something new, not as a result of forking, but of spawning off a thread. All right, so this is where we start descending towards hell, by the way, in this class. So that's Christian worldview. What's up?
So is there a difference between forking a child and spooning a child?
There is no operating system called spooning. So that would be purposely being inappropriate. There is definitely one called forking. But I would strongly encourage you when you're discussing operating system stuff in public to very carefully enunciate. Okay, very carefully enunciate. Forking.
So did I hear that?
The result of forking.
What's this?
I don't think anything can be birthed as the result of forking.
Not true in operating systems. In fact, it's quite common at any point in time for many children to be forked inside your operating system. It's
They birth everything, birth something almost every time.
That's what it does. That's what the fork system call does. It creates a new process. Huh?
It's got to get expensive.
That's a very old Unix thing, and we'll talk. It'll make sense when we show it. Just to give you the maybe the precursor for it. The way. So first of all, just what did you say?
You were talking about the forking that usually, unless the process is aborted, then there will be no.
I guess we're back to a chicken or the egg problem. So, but really where the system call where that name came from is, and we typically use multi-threading. We spawn off threads today. So the fork system call is a much older system call. But what you would do is you'd write a single program, and in the middle of that program, you would have you would make your fork system call, and it would return a process ID. And based on what the process ID is, the program would become aware of whether or not it's the original parent or the new child. And then you would have an if statement. If my process ID is 0, that means I'm the original, I'm going to do this stuff. If my process ID is something that's not 0, that means I'm the clone, I'm going to do this stuff. So there was a fork in the road as to who's going to do what stuff in there. But it's all still one program, one chunk of source code for doing it. So that's probably where the name came from, but maybe they could have called it split. Or Gen PID or something like that. So one thing you'll do in your next homework assignment, I think I glanced ahead, is you'll look at the comparison of system call names between Unix and Windows. So all of these operating systems are going to have a collection of system calls that the operating system understands. And they're going to have a whole lot of overlap in terms of what they do. Every operating system is going to have a mechanism for generating a new process. They're going to have a mechanism for killing a process, that kind of stuff. So now it comes down to how did they name them. So Windows names are far more appropriate than some of the Unix. Actually, really the only Unix name that's a problem is fork, but that's kind of enough, right? But you'll see, I think, Windows, the Windows names almost like spell it out, what it does, with capitalizations, create new child process, something like that. Okay, so that's basically the punchline. The punchline here is that things leave the CPU, I/O happens, then when I/O is done, things get back in line for the CPU. The CPU is one of probably is our major resource on our computers that we have to manage. And we want to make sure that the CPU doesn't get stalled. So we're not going to let a program run on the CPU when it's sitting there and waiting for, in the worst case scenario, a human being who's walked away from their computer. Okay, so if you imagine a real life example of that, if you're downloading a file in the background and then you're working with Microsoft Word and you've hit the save button, so Microsoft Word puts up the pop-up box for you to name the file, and you walk off. You want your download to keep going. Okay, you don't want the CPU just to be sitting there and waiting for the user to type something when you're at lunch. Okay, who knows when you're coming back? You got an 8-hour shift after lunch, okay? So it's going to be hours. So you come back and realize your download hasn't made any progress. We don't want that. Okay, we'd love for the CPU to get interrupted, and we'll just wait till the user finally types something, and then you can get back in line and get some CPU time. Make sense? All right. Direct memory access, this is something you maybe have seen called DMA on memory. So this is high-speed I/O devices able to transmit information as close to memory speed. So this is not actually using memory, our system memory, our RAM in our computers. Instead, it's creating a different channel for sending information between devices, between controllers, between things on our resources on our on our computers, without specifically going through system memory. So system memory, as we saw on the slide back here, is something that's shared amongst everybody. But we can have direct memory access where two different resources can talk directly to each other at, we'll just say, high speeds. Okay? And even though the channel might be technically slower than the re-write speed of memory, because you're not having to go through the operating system, request something from memory, and then get the response from memory, and creating a link that sends the stuff from memory back to you, sometimes it actually ends up happening faster, even though the...
Somebody got
Is that Dr. Locklear? Yeah, there may have been some forking going on down there. All right. What was I doing? Oh, yeah, so still talking about system call stuff, direct-to-memory access. I've already explained it. It's fine. All right, so storage stuff. All right, so we have a couple of different types of storage in our, when we talk about storing things in our computers. So when we think about memory, our system RAM, okay, this is for short-term, temporary, but really, really fast storage, right? As opposed to our hard drives, we expect that when we shut our computer off and we go home for the summer and we turn our computer back on, that all the stuff that used to be on our hard drive is still on our hard drive. So that's long-term storage. And with that comes the trade-off of typically being slower. But with that also comes the benefit of typically being bigger, right? So, you know, that's kind of our trade-off. So we have something called random access or volatile memory. So volatile would be the non-permanent, the temporary type memory. Okay, the volatile memory, just fancy way of saying temporary. Secondary storage is an extension of main memory that provides large non-volatile storage. Long-term, doesn't change, won't just disappear, that kind of stuff. But volatile, non-volatile sounds cooler. All right, so I could see me maybe asking a quiz question, something like, what's the difference between volatile and non-volatile memory? Kind of an important term because that is the kind of the de facto way of talking about those two different things. Even though from a human being perspective, we can translate them into short-term versus permanent, right? Okay, not guaranteeing that, but that would be a fair quiz question. So next time I decide I'm gonna come up with a quiz and I'm trying to come up with a quiz question as I'm walking into the classroom, this might be something I pull from. Okay, so magnetic disks, this is what we were talking about a little bit ago. So for us gamers or something like that, we're starting to move towards non-volatile storage that is faster. So we want to get as much speed out of our permanent storage as we can. And magnetic disks, we can kind of think about these things as our mechanical hard drive with moving parts. So moving parts has two side effects. One, they're typically slower. Two, they wear out. Right? Anything with moving parts is going to wear out. So when we have these magnetic disks, these things are spinning inside of that square expensive thing, okay, that you buy. And you know what is a hard drive? How many of you have you ever opened up a hard drive and looked inside of it? Okay, what do you see in there? Okay, you see the circular magnetic disky thing, right? What else do you see? Yeah, it looks kind of like a CD. Sometimes you have a couple layers. A couple, they're called platters. Couple of platters. Okay, so you see that. What else? Huh?
Like pinhead.
Yeah. The read-write head. So almost like a record player looking thing, right? Okay, and it's like 1 micron away from that. Okay, that's why it's really bad to drop a hard drive, especially while it's running. Okay.
Just shake those things.
Yeah. So and this is actually from a history perspective, this is a thing. So basically, if you had a laptop computer from, let's say, 10 years ago, I'm not sure when they put the safeguards in, but let's just say they didn't have them 10 years ago. As you get older, time starts going by a lot quicker. So 10 years ago was what, 2005?
Yep.
That really just seems like yesterday. That really doesn't seem like it was very long ago. But let's assume that was the case. if you were saving something, let's say you were downloading a file off the internet. Did the internet exist in '05? Okay. Let's say you were downloading something off the internet. Huh?
Chrome didn't.
Yeah, Chrome didn't. Now, did the internet exist since you guys were born? I remember before the internet. Life was so boring. In the dark times. Like, what did we do? I remember before cell phones.
What'd you read when you went to the bathroom?
In our bathroom at our house, we had like a magazine rack thing. Yeah, what the heck? Took up vital leg room.
What's a magazine?
What? You mean there was something other than toilet paper in the bathroom? Some other kind of paper?
Backup toilet paper?
What is this backup toilet? Yeah, so we had Sports Illustrated. Does that magazine still exist? Sports Illustrated?
Yeah.
Okay.
They do swimsuit issues.
That's all you're aware of, is the fact that there's an existence of a swimsuit issue.
Which says something that even with the internet, you still keep track of the swimsuit issues.
I think that's on the internet now, though, right?
You can get it on your phone.
Okay.
Yeah. So really what you're saying is the print version of that is just for the dirty old people.
Yeah.
Makes sense.
The digital copy is for the dirty young people.
Okay. Got it. What was I talking about? Oh, the magnetic disk. So anyways, let's say you had a laptop from 10 years ago, something like that, and you were downloading a file, and so the hard drive was writing something constantly, and you drop that laptop, toast. That hard drive, 99.99999 infinity, okay, chance that hard drive is gone. Because that read-write head is constantly, and as soon as you drop that with the forces, just scrape the crap out of that magnetic disk, gone. So what they started doing is they started building like the precursor to accelerometers into these hard drives for laptops, where what it would do is if it detected something bad, everything would just lock. And just hold on for dear life. Okay, so I mean, you would probably still damage the hard drive if you just reached back and spiked it. And which would be kind of funny. Because don't they usually haven't they done that for some of like the iPad launches and stuff like that? If somebody waits in line for 20 hours, but they work for some company. And they walk outside, they unbox it, and just immediately spike it into the ground, just shatter it out. And everybody in the line is like, what did you just do? I find those hilarious. Actually, what I really find hilarious is last night Levi sent me a video. I'll just leave it at that.
Back to 14 children.
Yeah, no, it was like a whole bunch of like people falling down or flipping off stuff, like standing on something and falling off, and but what somebody did is they photoshopped in or video edited in like this little ninja guy, that would like karate chop him or sword stripe him straight. And sometimes you got so focused on the ninja you didn't even know what ended up happening to the person, and after the fact you'd wonder how did they even fall like that. There was a couple where like this lady was just walking down the sidewalk and the ninja would come in and like punch her in the face and she would fall down, but the ninja wasn't real. So this lady somehow acted like she got punched in the face and just fell down with nothing happening around her.
They do that with whoever does the RKOs.
Oh, John Cena.
It's John Cena.
They walk and they fall forward. He just comes out of nowhere and RKOs.
Oh, apparently I need to see this.
Yeah.
So somebody's got to send me a video for that.
There's a whole subreddit dedicated to those. / wasted GIFs is pretty good too.
RKO out of
Yeah.
Yeah, I stole a funny line yesterday during a Bible study. We were talking about John the Baptist and the beheading thing, and I used I said, John the Baptist, bobblehead night, some assembly required thing from the Harry Carey calls the first baseball game. If you haven't seen that, you should watch that. Okay, so in any case, magnetic disks. They're old mechanical hard drives where things are physically moving, they're going to wear out, blah, blah, blah. So rigid metal or glass platters covered with magnetic recording material because that read-write head is constantly, writing stuff to it. The disk surface is logically divided into something called tracks, kind of like a record. So this is an evolution of a record, which are subdivided into individual sectors. So within a ridge, if you will, within a track, you would have individual little sectors. Think of it like an array with little buckets. And each sector was a bucket in that array on that particular track that could hold something. Okay, and a sector is going to have a certain size. All right, so we were talking about what's inside of that hard drive. So we opened up the hard drive, we see the CD-looking disky thing, we see the read-write head thing. What else do we see in there? Okay, the thing that controls the read-write heady thingy. Okay, what else?
Isn't there a laser in there?
It's not. I don't think it's exactly a laser. It's a magnet that pulls bits in. And, yeah, so go higher level than that. So we're done with the read-write head part of it.
The case some circuitry.
Okay, we got the case. We took that apart. What's at the very back of every hard drive?
There's some circuitry on there.
Okay, what's that circuitry for? Controller. Okay, so we have an interface controller, and that controller, the circuitry you're talking about, that knows how to run that read-write head, correct? So that's what it knows how to do. So think of it like a forklift. So the controller for a forklift is the dude or a dudette. Is that still a thing? Dudettes? Whatever. Okay, sitting in the forklift, working the arms to make the forklift dig stuff, right? Okay, so that's the controller. So that's what that circuit board is. That's the person, if you will, that knows how to write and read stuff from that hard drive. And then on the back end of that is what? The actual interface that's going to live between that physical hard drive and your computer. So when we think about our hard drives, what are our possible interfaces for our hard drives today? Okay, serial ATA. Okay, true, but not today, right? So an IDE interface is the gray ribbons, right, from a long time ago. But during my lifetime, I don't know about during your lifetime.
No, I've seen people bring like those into our store for
Are you serious?
like computers with ID hard drive.
Okay, what store is this?
PC Clinic is a
Oh, okay, I thought you were gonna say Radio Shack or something. Have you ever been in a Radio Shack and not been creeped out?
they have a business now.
Are they all out of business?
Yeah. There's
Well,
like
that could be.
maybe a handful.
No, there's some in malls still.
I don't know, but the one in Grafton.
Then
Yeah.
it's soldering.
They're slowly dying that good death they need to.
Oh, whatever. So, so IDE cables. IDE would be a possible interface. So we have serial ATA, we have IDE. What else? SCSI, also old. You know what SCSI stands for? A small computer serial interface. It's the predecessor to serial ATA, actually. So something we'll talk about in here is the difference between parallel and serial. Parallel and serial. Historically, parallel was faster. We would think parallel was faster. Serial was slower because serial sent things one bit after another. Parallel would send things in bursts, 8 bits at a time, for example. So our old hard drives, IDE, is a parallel technology. SCSI is a serial technology. And certainly for a long time, IDE was the popular one, right? SCSI was only really used for server-type machines. Consumers, it wasn't really a technology consumers used. But now we use a serial technology with our hard drive, serial ATA. It's kind of interesting. What else? Another examples of serial versus parallel is what's going to come up next when you guys give me the next answers for your possible interfaces between your computer and your hard drive. Go
Are you
ahead.
talking just internal hard drives?
Anything, any kind of hard drive.
Some of the externals connect by USB.
Okay, USB, certainly. Yeah, we connect to them through USB. And if you open up that external hard drive, what are you going to see? You're going to see an extra little interface that's going to convert between USB and SATA. Right?
Solder
You can get
with solid state drives.
Oh, okay. That is an interface, but it's fine.
eSATA now too, right?
Okay, well, what's the difference between SATA and eSATA?
You can connect. I don't know.
eSATA is like USB.
Yeah.
eSATA is a serial ATA interface, but instead of being inside of a computer has an external SATA port that you can connect a serial ATA cable from the back of your computer into a SATA input on the back of your external hard drive, for example, and then it doesn't require a special interface inside because it's SATA to SATA. And it's faster, right?
Yeah.
SATA is faster than USB. That's fine. So currently SATA, I think 6 gigabit per second is kind of your advertised top speed for them. USB 3, what's USB 3 now? Is it 1 gigabit per second?
5 gigabits a second.
USB 3 is 5?
Oh, that
Oh, okay. So almost the same speed.
It tells me. 3.1 is 10 gigabytes a second.
Okay, but USB is going to still be a parallel technology versus SATA is a serial technology. And we'll talk about the pros and cons of each of those. One's not necessarily better than the other. They both have benefits and weaknesses. Okay, so we have USB. What else do we have? You said eSATA, still SATA.
SAS.
SAS? What is SAS?
It's a serial attached SCSI.
Oh, serial attached SCSI. Okay, so is SCSI making a comeback? Is that kind of what that is? Are we just making stuff up from the Google? Okay, all right. What about FireWire?
Thunderbolt.
Yeah, nobody.
FireWire's kind of gone out of vogue, right? As Apple's adopted USB for everything now. Before it was Apple was FireWire and USB was everybody else, right? But FireWire is actually a serial technology and USB is a parallel technology.
USB-C.
Yeah, when it's USB-C.
Yeah, well, USB-C is the same thing as USB. It's just a smaller connection that allows for multiple, either way, but also multiple, so easier plug, but also multiple channels within one without significantly degrading your performance, I think. 87% sure about that. So FireWire, I heard somebody say Thunderbolt, Apple's high-speed, dealy, flippy, majiggy. Okay. So in any case, we have all sorts of various interfaces, but at the end of the day, the hard drive itself today is likely going to be a serial ATA hard drive.
Bluetooth one, too.
Potentially. I mean, there wouldn't be a major reason why you couldn't have a Bluetooth interface to an external hard drive. I mean, so in fact, I'm sure they exist actually, and also Wi-Fi. You know, so we think about those controllers. So you're going to have the hard drive. The hard drive's going to have that circuit board, that controller. On the back end of that is going to be serial ATA by a modern hard drive standard. So let's just say all of our modern hard drives are serial ATA hard drives. Well, now you either directly connect in through serial ATA or you're going to have another controller that's going to handle the conversion between whatever way it's the connection's coming in from the computer to the serial ATA. So that connection could be USB, could be FireWire, could be Thunderbolt, could be Bluetooth, could be Wi-Fi, could be anything, really.
HDMI.
It could be HDMI.
I've seen them.
It would be weird, but it
Yeah.
could be. Could be.
We found one at work yesterday. HDMI to USB.
All right, but does that kind of make sense? How it all works? All right, so that's our magnetic disk stuff, but unimportant. So the magnetic disk aspect of this isn't really what I want you to get out of this. It's that whole what's the role of a controller versus the physicality of the device. Okay? We've already talked about this. Storage systems. We have a combination. The first two are the big ones, right? Speed versus cost. Faster the speed, very, very, very likely the higher the cost. Okay, and then the volatility thing deals with short-term versus permanent type stuff. Typically, when we see the word cache, we want to think about small storage, fast speed.
I just think Johnny.
Not spelled like that. All right. So here's our speed hierarchy. We've already mentioned some of these. So the very fast, this is going to be our registers. These are the hardware variables that live by the CPU. Okay, it's very balmy. This is tropical conditions here. It's going to be very warm where the registers are. Then you have your various caches, L1, L2, L3. Then you have your main memory. Then you have your electronic disk. So this would be something like the flash-based solid-state drives, that kind of stuff, I assume is what they're talking about there. Magnetic disk would come next. Then your DVD, CD type stuff, your optical disks. And then lastly, magnetic tapes for like large-scale backups.
What is a magnetic tape?
Well, it looks kind of like a cassette tape, but it allows places to do like what a lot of businesses will do for when they have to follow like HIPAA laws and stuff like for like medical stuff, is they'll have a physical tape backup of their machine each night, and then they take the tape out and put it like in a firebox, something like that, because they can't store the stuff off-site or transfer it off-site because it's medical records. And so very slow, but typically you're going to have a big capacity.
Didn't Sony just come out with a new one last year that is like a crazy amount of space?
It wouldn't surprise me. Yeah, but I mean, these are very specialized tasks. Like my dad's dental. My dad's a retired dentist now. Well, he is a retired dentist. But when he had his office, they did a tape backup every night because I mean, he didn't really know how to do it offsite anyways. But they do have to follow medical laws, and realistically, he probably could have done an offsite backup and not gotten in trouble. But legally, I think I don't know the exact rules, but if you guys are ever interviewing for jobs or something like that, and somebody references something called HIPAA laws, those deal with data security associated with medical-like data. What's the proper way of handling that kind of stuff?
Any medical data, actually.
Yeah. It's typically used in medical.
Because nothing else is protected.
Right, yeah. That's all that's protected, and even that's not protected. All right, so that's our hierarchy stuff. We've already mentioned that. Talked about the caching, different speeds. Okay, so system architectures for our computers. So most of our computers, and this is a little bit dated, are going to use a single physical chip. And this is going to be a general purpose processor. We've already kind of talked about this a little bit when we were comparing our CPUs to like our GPUs and our graphics cards. So our GPUs we might have 1,000. 1,024 multiple GPUs in a single graphics card. But those aren't general purpose processors. Those are very special purpose processors that are really, 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 really good at doing floating point math. All right? When we think about our Intel Core i7 or Core i5 processor, our modern machines maybe have 2 of those in them, 2 cores. But they're general purpose. They know how to do a zillion different things, not just floating point math. All right, so most of our stuff have one processor. Modernly, they have one dual core processor. Some of them have more cores than that. But these are general purpose for solving large classifications of problems. Most of our systems also have special purpose processors as well. So, for example, in the iPhones have a general purpose processor. And then they have their I think it's called the M5 chip now, but that's their motion coprocessor, right? Which is actually, I think they moved that onto the chip now, but whatever. So they have a secondary processor in there whose job it is to do motion sensing stuff. So it has stuff on it just for that. Most of our mobile devices are going to have a secondary CPU, a secondary processor for dealing with stuff coming in from Wi-Fi. Any sort of network type stuff. So that processor's entire job is going to be dealing with compressing and decompressing and unpackaging network packets, that kind of stuff. So a very specialized task for that. Let's see. So again, multiprocessor systems, we're pretty familiar with these. Every time you buy a new computer, we have more than one processor on them, and more than one processor isn't necessarily better than one processor. I've used the example probably in the past that, if you have 16 cores, the real life example is how many people does it take to change a light bulb? Okay, so if I can change the light bulb at speed 10 and the rest of you are going to gang up on me and you're going to race me in changing a light bulb, but the fastest one of you can change a light bulb at speed 9, I'm going to beat you. Because changing a light bulb is a one-man job, okay, one-person job. But if we're cleaning up a park, even if I'm capable of cleaning up a park at speed 10, whatever that means, and the rest of you are capable of cleaning up a park at speed 9, you're going to beat the crap out of me, right? I'm going to still be there till midnight, and you guys are going to be done in 45 minutes. Because you're going to be able to separate that task out and each take a portion of the park. Okay, so certain tasks where you can divide labor up really benefit from multiple processors. Other tasks, we want the fastest single core possible. Okay, so that's really what we're talking about here. The economy of scale is what we really just talked about. Okay, so modern computers from a thread perspective. So again, we want to think about this in terms of resource management. So we have a device, a resource. Okay, and this device we have, so here's our instructions and our data. So this is how we tell a computer what to do, and we use our memory, our volatile stuff for short-term storing the values of our variables, that stuff. Okay, so here's our instruction execution cycle. So this is as stuff leaves the hard drive, goes into the cycle for talking to the CPU, things get buffered up in some sort of cache, so the next instruction is staged, ready to go into the CPU. We can have data moving back and forth between these, because sometimes you're going to be moving something from here into like a register or L1 or L2 cache over here. So, we have different things moving back and forth here. In the middle, we have the idea of our thread of execution. So generically, this is just our CPU. Okay, so this is where stuff is executing, and we can spawn off threads in here, but really this is just talking about our CPU, and we might have multiple CPUs. That's what the star N is talking about, the number of CPUs we actually have. All right, but then we have all of our other stuff that's occurring here. So we have input-output requests, we have data requests, we have interrupts where the CPU is told to shut up, and ultimately all this stuff is going to be interacting with other devices on our computer, other resources on our computer. Make sense? So this is the high-level life cycle of how things move around inside of our computers. Yep. DMA and bus. Okay, well, DMAs are direct memory access. So this would be this device having direct access to our hard drive or something like that. So information moving directly here rather than having to request data through here, then data being requested back through here, moving back through and delivered here. Yeah, this is a shortcut. The bus in general, when you use that phrase bus, which isn't on this screen, really deals with how all your devices directly interface with memory, with RAM. That's our bus. So memory is this thing that's sitting up there. Okay, so let's say the memory in this room is this projector. Okay, and the bus in this room is the air. And any one of us we can jump up and access that projector using that bus. Make sense? Okay, we're out of time. Okay, so we'll start, we'll start with symmetric multiprocessing architecture next time. We'll zip through the rest of this and then dive into chapter 2. Sound good? All right, I'll see everybody on Friday.
Grab your opinion on my